I'm Jim Kircher. We're starting with a story about modern plant science, but it got me to thinking about Gregor Mendel, the 19th century monk and father of modern genetics. He did field work, crossbreeding pea plants in the monastery garden, did a lot of careful observations, did some math, and voila, genetics. And then it took 50 years before its importance was recognized. These days in science, the research, the breakthroughs, the applications, they're happening and being shared and applied at a much faster pace, with a lot more technology. This is the Danforth Plant Science Center's new Phenotyper. There's only a few like it, and as advanced as it is, the work here is still, as it was in Gregor Mendel's day, about plants, about observations, and data. This machine runs plants through a series of sensors that record characteristics, that is, the phenotype, in ways the human eye just couldn't do. We'll get back to this machine in a bit, but it's part of the $45 million expansion of the Danforth Plant Science Center, a nonprofit research institution founded in 1998. Along with local companies, universities, and the Botanical Garden, it's a big part of St. Louis's role as a center for plant science research and application. The new wing of the center near Olive and Lindbergh has space for 100 more scientists. It had its grand opening in mid-April, and President Jim Carrington gave reporters a tour and explained what went into the design of the lab spaces.
We have lots of different scientific groups in the same space. We wanted people to collide and interact all day long. We didn't want people to be sequestered in their own offices or in their own rooms. We wanted them interacting because those collisions, those frequent interactions, are where ideas are shared on the spot in real time, where solutions are...
We sat down with Dr. Carrington to talk about this institution, which a lot of people have driven by and heard of, but don't always know exactly what it is.
The Danforth Center has a mission to improve the human condition through plant science. That means we want to improve our ability to feed people through agriculture. We want agriculture to be more sustainable. We want to see the private sector develop. So we want discoveries here moved out to the private sector. We want to train the next generation of scientists. So when you look at the impact that the Danforth Center has had, we have about 1,000 scientific publications that we've put out into the public domain that helps understand how plants work better. Some of that information gets used to build better plants. Some of that information gets used to develop new companies. Starting those companies is a big part of what we're here to see happen. It's important to point out that if we don't commercialize discoveries here in the United States and in developed countries, the discoveries that we make here don't make it out into the real world. And what can we do to relieve hunger by making agriculture more productive with fewer inputs like water and fertilizer?
And that's particularly important, I would think, in terms of climate change, not just in sub-Saharan Africa, but in North America as well.
That's right. Everywhere that you grow crops productively today, everywhere is going to be impacted, or is going to continue to be impacted by our changing climate. Dry areas in the Southwest and on the West Coast of the U.S. are going to become drier. The Midwest is going to change. Some places are going to get more water, and you're going to have different challenges with that. What we know, because we've measured it already, is that changing climate changes the land, it changes what can grow, it changes local habitats, and it changes what you can do on the farm. Science has to keep up with that. There's no choice there. That's our imperative moving through the 21st century and beyond. We've got to adapt to climate that is changing. And if we don't make agriculture more resilient, we're going to suffer the consequences.
In some ways, plant science still looks like what you'd expect it to. But now they've got the technology, the data crunching, the gene sequencing, the ability to alter a plant and test it under different conditions. But observing the changes in a test plant's phenotype, its physical traits, that was always a bottleneck. And that's why researchers are now lining up to use the new Phenotyper. Scientists running this experiment want to know how rice plants react to various stress factors, drought, extreme temperatures, mineral deficiencies, things like that.
And it's a very special facility. It can house 1,140 plants. So they grow in a very controlled environment. That means we can manipulate that environment. So we can say high light, very, very hot. We can also impose very controlled drought.
Each plant comes out of the growth chamber and goes into the machine. It undergoes a battery of high-tech measurements and observations, size, weight, color, shape, a day-to-day report on the plant's response to the conditions, and it goes right into your database.
One really hard thing about plant science traditionally is that you have to destroy the plants when you want to measure them. You know, if you wanted to say know how much mass there is on that plant, you'd have to cut it and then weigh it. With this system, instead of destroying the plants, we can take images of those plants and then model the weight. So we don't have to destroy those plants, so we can measure them every single day and look at them through their growth cycle.
We use a lot of technology here because plant science today is a technology-intensive science, just like biomedicine is technology-intensive. In 10 years from now, we want to still be using this building, obviously, but we're not really sure what kind of science we're going to be doing in 10 years. We might not need all these benches. We might need gizmos and widgets that haven't even been invented yet. So we wanted the flexibility to adapt over time to do the cutting-edge science that we always want to be doing.